And we are live. Live, there's the button, live. Hi, ast111x, summer 2017. I'm Frank.
And I'm Becky.
And we're going to chat a little bit about some astronomy and solar system stuff over the next 40 minutes to an hour or so. So let's go ahead and start off. We're just going to chit-chat a little bit about current stuff. So always current stuff is sort of, what kind of astronomy do you do? So Becky, what kind of astronomy do you do?
So I'm a graduate student at Arizona State, and I study extrasolar planets. That's planets that go around other stars.
Cool.
And I also work a lot on the kind of cameras and telescopes you would have to use in order to study those planets. So
are you trying to do like direct imaging of them, or?
No, directed imaging is really hard because stars are really bright, the planets are very dim. So it's really hard to tell the difference when they're really far away. Okay. I use the easiest method of detecting them, which is basically if you have a star out, however far away, and the planet actually passes in front of the star while it's orbiting, the star is going to get dimmer. And so if you watch a star very, very, very carefully, and you measure just how bright it is, then very regularly it'll dim just a little bit. And then as the planet crosses over, it'll brighten up again. And if you notice that happens really regularly, then you've found a planet.
How big are those? How much does it dim by? Is it like 10%, 1%?
It's usually like 0.1%. Because like if you look at the size of the Earth versus the size of the sun, it's minuscule.
That makes sense.
Which is why actually we tend to detect planets that are more like the size of Jupiter and bigger, because the size of the planet is actually somewhat closer to the size of the sun. One of the reasons we have such a hard time finding Earth-like planets around other stars is the fact that they're so small, that they just don't make the brightness dim very much, and it's very difficult to see. The other problem is that the Earth only crosses in front of the sun once a year, and it's much easier to find planets that are much closer and therefore cross much more often.
Right.
So, but we actually are using, a big part of the research is the fact that astronomy is really expensive because we have a lot of specialized telescopes, a lot of specialized cameras, right. But commercially made telescopes and cameras are getting good enough, precise enough, that we believe that we should be able to make scientific measurements using those. And if we make it work, it's literally 100 times cheaper than those really big experiments.
So how far along is your camera?
The camera itself, we have detected a planet.
So it's operational.
Yeah, the problem is
you've had first light.
Yeah, it actually does work. The problem is our telescope, the commercial telescope, has been finicky. So
a Celestron or a Meade or something along those lines?
It's not a Celestron. The Celestron is the one that we actually managed to get to work.
Okay.
It's an 18-inch, which for a commercially made telescope is really, really big. The mirror itself is 18 inches wide. But it's very, very, very tall, and so it's very windy, and the wind is enough to make it shake all over the place.
Rattle and roll.
So
no dome. You don't have it in a dome.
Yeah, the problem is that we have it in a place where the dome cannot be permanently set up.
The dome rattles around.
It's the fact that we don't own the place that the telescope is set up on, so we have to keep moving it away and then moving it back.
Your tenants.
Yep.
Your itinerant tenants.
Yeah. Okay. It's like, this is the thing that people don't think about when they set up telescopes all over the place, is we have to get permission to be there. So cool. It's a pain.
When are you going to graduate? When will you be Dr. Beck?
It's going to take another couple of years because of the setbacks with the telescope. But we're also thinking, one of the reasons we're looking for the cheaper or less expensive cameras is that there's a lot of smaller telescopes that people aren't using very much anymore because they want to use the big fancy telescopes.
Okay.
And what we could do is take our cameras and put them on established telescopes that are not being used for much else.
Yeah.
And so those are stable and they stay where they are. So we could set them up and they would be able to not be affected by silly things like wind. and right now our telescope's in a place where light pollution is a problem. So
you said you're doing infrared?
Yeah.
Why IR? Stars don't shine in the IR.
Oh, they do. A lot of the stars, like the most common stars in our galaxy, are actually dimmer than the sun.
Okay.
And their brightest wavelength actually is in the near infrared, which is light waves that are a little bit too low energy for our eyes to see. And those small stars, because they peak in that wavelength, that means that when the planet passes in front, that's when the lowest dip, most obvious dip is going to happen. And because those stars are so small, the planets are closer in size.
Right.
So they'll block more light and the dip will be more obvious.
Cool.
And there's also the infrared. In order to figure out whether there's life on planets, we need to know what the atmosphere of the planet is like. Right. And there's a lot of things we can learn about a planet's atmosphere using the infrared to figure out if there are signs of possible life.
Cool. And we cover light next week in this course, so some of what Becky's
You'll learn a lot more about what near infrared and infrared light is.
There you go. Okay, so what do I do? I basically do stars. I'm particularly fond of stars that go boom in the dark night sky, and so I admire their fireworks that they make. But in the process of making fireworks, they also make elements, which ultimately come down to making you and me. And so I find that whole topic sort of fascinating. So that's the general astronomy topic that I work on. And I'm a theorist. I make it up as I go. I do a lot of calculation. I do a lot of software. So yeah, that's a little bit about what I do. Okay, so why don't we put up a thread on edX, and we had a number of questions. And so why don't we start answering some of those? Oops, I'm in the wrong space.
You guys should be able to, those watching should be able to post chat messages if you guys have questions. And if we have time, we can get to those too. So.
Hey, I think your advisor has joined the chat group. I know.
Hey.
Okay, so why don't you pick one of the questions that were asked and I'll follow.
Okay. First question I ran into was, why do all of the planets move on the same plane? And this has to do with how stars and planets are formed in general, like the whole system's formed more or less at the same time. So stars form in these big clouds of gas and dust. If ever you want to go online and look up the Orion Nebula, that's one of the closest really cool systems of stars or clouds and nebula that has stars forming in them. There's also the Horsehead Nebula. There's a lot of cool stuff. So when you have all of this gas and dust, it's all moving in random directions, but it's actually highly, highly, highly unlikely that there's not a sort of general direction, like the mass is going to move a little bit more in one direction than another. And as it starts to collapse, it'll start to rotate. So think about like if you have a weight at the end of a string and you start to spin it, it starts to flatten out into a disc and it rolls like that. So as the cloud starts to collapse, it'll start collapsing down into a disc and then start collapsing inward. But because it collapses down into a disc, the planets that are formed in that disk of cloud of gas and dust. So most of the stuff, the big planets in our solar system are from that disk. A lot of the comets and asteroids and stuff, though, they're in a cloud just all around left over. So it's just the big stuff that tends to all be in that disk. Does that make sense? Did I miss anything?
No, I think that was great.
Cool.
Almost like pizza dough.
Basically, yeah.
Flattens out. Okay, I will take, there's two questions that are the same. They were kind of the first two, so I'll just read the question and then I'll yammer for a little bit. In the Sky Dances lecture, I don't understand why we had to model the sun as rotating around the Earth in the celestial sphere model of the stars. And then the related question underneath it kind of went, yes, I too didn't understand that Earth revolves around the sun. But how come the sun rotates around the Earth? Please explain. And how does the zodiac signs come into the background of the sun? Okay. Well, if you just walked outside and you just looked at the night sky or the day sky, you too would conclude that we are at the center and everything is moving around us. So it was completely natural for antiquity to set up that kind of a model where we're at the center, the sun goes around on the celestial sphere around us, the whole celestial sphere turns, all the planets do their dance on the celestial sphere. So putting us at the center, it agrees with everything you can see with your naked eye. So it's a very natural model to first gravitate toward.
That's why the ancient, like, historical references, everybody thought that the Earth was in the middle of everything, is because it looks like
it absolutely looks like it. The fact that the explanation is a little bit more sophisticated and what you see is not necessarily directly reality, that took quite a while. But you know, the Greeks considered the idea. They considered the idea that maybe the sun was at the center and the Earth went around. And they realized that if that was true, then at various, if the Earth went around, then the Earth would be closer to the celestial sphere at different points. You'd be different on different sides of the celestial sphere, you'd be different. And so you expected to see an angular difference in the stars, AKA parallax. So it's kind of like your left eye, right eye. You know, 6 months you look at a star and you'd see it at one position, and 6 months later it'd be like your right eye and you should see a jump in the star, just like your finger. If you put your finger in front of you and go left eye, right eye, you see your finger jump back and forth. This is something we do in the lecture.
The original theorists.
The original theorists, that's right. See, we make it up. So the Greeks had the right idea. That is exactly correct. But when they went out and looked for parallax, they didn't find any. And so that left either two conclusions. Either, well, there were several conclusions. Either the stars were just unimaginably far away, and they couldn't imagine the stars could be that far away. So there was no effect. So either the stars were ridiculously far away, or the model was wrong and the Earth was at the center. And for a number of reasons, they adopted, like all those that came before them, to go with the model that the Earth was at the center. But the seed of that idea was there. And there's a great book by Alan Hirschfeld called, I think it's like The Race to Measure Parallax, you know, putting the third dimension on the sky. And it's a great story of humanity's hunt for parallax, which actually was not done until the 1850s with Bessel, who measured, if you let me think a minute, I'll remember the exact star he measured. But in fact, it turned out that the stars really were much farther away than the Greeks had imagined, and they just did not have the technology to measure that. And that technology really didn't come around until the 1850s. These days, parallax is big business. We can measure it routinely, rather finely. and it is indeed how we put the third dimension on the sky. So the only reason that, you know, you believe that the Earth goes around the sun is because that's been drilled into your head since kindergarten. Because that was a revolution when it was finally nailed. No, we actually go around the sun. And so that's why it's told to school children, because the point being, not that it's just true, but that everything isn't always exactly as it looks. It looks like we're at the center and everything goes around us, but that's not true. So, you know, the ancients were not dumb. They were just as bright as we were. And if you go out and look, it's the most first order zero thing you would do is say we're at the center and everything goes around us. Okay. Becky, why don't you go?
A very, very similar topic to what he was just talking about is motion on the celestial sphere. There was a question about what was meant when Frank was talking about if you're at the 40th latitude and something's straight above you, but you're elsewhere, it wouldn't be the case. He wasn't talking like a specific thing. It's that depending on where you are on Earth will change what is directly above you, because what your reference point is yourself, because the Earth moves and you're using yourself as a stationary point, so it looks like everything else is moving around you. And because the Earth is at a specific angle, where you are on the Earth dictates how I couldn't find a great picture for this, so it's very hard to say in words. Dictates how the stars move across the sky. And nifty pictures that you can find if you look this up is if you leave a camera such that it is continuing to take in light as the stars move, you'll see that the stars move in streaks and straight lines across the sky. It's just that the angle at which they rise up and move across and come down depends on what your latitude on the Earth is. And it's kind of nifty. You can actually read what latitude you are at just by figuring out how high the North Star is above the horizon. Here in
the Northern Hemisphere.
In the Northern Hemisphere. Technically, you could do it in the Southern Hemisphere, but you'd actually have to like look through the Earth to see the North Star, which obviously is not going to work out for you.
Yeah, well, because there's no South Star, right? Yeah,
it's actually like a void. Like if you look up in the sky, it's just sort of an empty spot. Mm-hmm. So we got lucky with the North Star. Southern Hemisphere is much harder to deal with. So
I think one short way to say that is the altitude of the North Celestial Pole is equal to your latitude, right? Is that about right?
Yeah. I should have brought
this. You're the observer.
No, you're right. And now that you just said it like that, we actually have this cool little contraption that's basically just a regular protractor with a weight, and you can measure the altitude of the stars that way. Yep. I never thought of it. We have them somewhere, but not right now. I'll post a video. I think there's a video somewhere about how you can measure the altitude of the North Star and then figure out.
Protractor, absolutely.
Yeah. I think that's part of what a sextant is, actually.
That's right. That would be a great project for somebody to do for your outdoor #1 activity. Somebody wants to do something fun there, that would be cool. Measure your latitude by measuring the angle of the North or South Celestial Pole relative to you. Cool. Okay, let me pick one. Let's see. Oh, I really didn't finish that other question off. So yeah, so once you figure out that the sun is at the center and the Earth goes around, or in the celestial sphere model, if you want to put the Earth at the center and the sun going around, the sun doesn't go all over the sky, right? The sun doesn't appear up at the North Celestial Pole. The sun follows a very definite pattern. And the constellations that the sun happens to go through, and there are 13 of them, not 12, those are just known as the signs of the zodiac, because you don't find the sun up at the Little Bear, or up at the Polaris, up at the North Star, right? It follows a certain band. And so all the constellations in that band just happen to be known as the zodiac.
An interesting way that I had it looked at is if the sun never rotated at all, the only reason that not the sun, I'm sorry, if the Earth didn't rotate as it orbited, if it just always faced the same direction.
Okay.
When the sun moved around the Earth from our point of view, when it looked like the sun was moving around, it would take an entire year for the sun to go around, and the constellations it would move through while it was moving around for that year would be the signs of the zodiac. So it's just the relative position of the sun as you go changes a little bit with time. So what constellation it's in front of will change over the course of the year.
Right. Cool. Yep. Yep. And of course, the ancients were quite well aware that there were 13 constellations, but that didn't quite fit in with 12. So what is the myth? Oh, here's a question for you. What is the missing constellation? All right, that is not associated with a month. Let's see who can figure that one out. It starts with an O. There's your big hint.
I always remember that, but then I never remember exactly how it's spelled, so I can't say it.
Yeah, it's got kind of a funky spelling, that's for sure. Okay, what's another question? Can you explain the difference between the 27-day lunar phase and the 29.3 lunar month? I keep getting the two confused. Sure. So this has gone over in the week 2 material, but we can do a little bit live here. So again, this is sort of an example of what you see is not necessarily what is. Okay, so what you see is that the time to go to full moon is 29.3 days. That's why it was the basis of month, which has as a root word moon. So full moon to full moon is roughly 29.3 days. It varies a little bit. It varies because the moon's path is not circular, it is elliptical as it goes around. So that's what you see. But that is not the true period. So this period, this 29.3 days, is called the synodic period. But it's not the real period. It's not the period you would stick in like Kepler's law or Newton's law of gravity. So the real period of the moon is the 27 days. And what do I want to say about that? That is called the sidereal period. You can also sidereal, so it's the real period. That's how I remember it. Sidereal is the real period, the one you would stick in Newton's law. And the reason they're different, right? So the true period. So if you line up the moon and the Earth with a star, a distant star, and the Earth goes around in its orbit, the moon goes around. By the time it comes back up, by the time you get the same Earth, moon, star alignment, that's the real period. That's 27 days. Okay, that's the physics period. But because the Earth has moved around in its orbit a little bit, the moon is not full. The moon's at some angle, and it takes an extra 2 days for the moon to come back around, such that it's lined up with the sun, and you're back to a full moon phase. Okay, and so that's why the synodic period is longer, simply because the Earth has gone around in its orbit, and it takes the moon. The moon has to go around a little bit farther to catch up to get back into the full phase. So I hope that helps that discussion a little bit between synodic and sidereal period of the moon. All right, you want to take one, Becky?
Okay. Another one that was asked, interesting. Is it not working?
You just disappeared. Oh, you're back.
It's is it showing the PowerPoint at all?
No, I think you have to do a screen share.
That's what I thought I was doing, but when I tried it,
yeah, try it again.
oh, it's just going entire screen.
Oh, there we go. Okay, I'll shut up so it doesn't flip back to me.
Okay, so basically, The reason for the tides is that when you have a large body, the area that's actually like closer to the other body is pulled on harder by the gravity than the area that's the furthest away. So if this was the moon and this was the moon's gravity would pull harder on this side of the Earth than it would on this side of the Earth. So these arrows represent how much the gravitational pull is affecting the planet. So the reason for the tides is since this is pulled harder than this, it starts to cause the planet sort of to stretch out in an ellipse so that it's the diameter this way is longer than the diameter this way. And so that's what causes the tides. And the reason that we have ocean tides is because since the oceans are liquid, they're able to stretch more than the Earth, like the rock and the ground. It does actually have some of a tide. This does start to turn into ellipse a little bit, but the ocean, because it's fluid, is able to be pulled on more by the moon. And so as the moon goes around, you have this sort of extra amount of water pulled in that direction, and it just moves around with the as the Earth rotates. So, and the reason that certain tides are larger than others is that for the most part, the biggest influence on the tides on Earth are caused by the moon, because even though the moon's much smaller than the sun, it's much, much closer. But during a new moon, the moon and the sun are both pulling in the same direction. So the gravitational influence of the moon and of the sun are both pulling this way. So there's even more of a pull on the water to move in this direction. So it's just basically during a new moon, the sun and the moon are teaming up to cause even more gravitational pull on the oceans. So that's the big thing and for the rock and the everything in the Earth, the tidal forces are so small that the changes in the level of the oceans is pretty significant, obviously. So so basically, yeah, that's the big thing. And depending on whether the sun and the moon are cooperating with each other or not depends on how influences on how good the tides are, how big the tides are. So that's pretty much it. Wow, that was interesting. Okay. That should basically answer that question, I hope. If not, just definitely post more specific parts about what you don't understand on the feed. So that's pretty much all I had to say. I'm actually running out of questions that people asked.
I have to unmute my microphone or nothing happens. Okay. Let's see. Let me. Hey, we got a solar eclipse coming up. Are you going to go see it somewhere, Becky?
I am going to be able to see parts of it, but it's like not going to be in the right place. What?
Are you going to travel anywhere to see it?
No. I made plans to travel before I realized and I had time to plan for the solar eclipse, so I'm going to miss the best points of it since it's only visible. Like a total eclipse is only visible in certain places, and it's like what, Missouri and sort of that band in the central U.S. Are you traveling to see it?
I am actually. I will be going to Sun Valley, Idaho. So if you happen to be in Sun Valley, Idaho, say hi. And the reason I'm going to Sun Valley, Idaho is because the American Astronomical Society is having a meeting there on high energy phenomena. So like things that explode. So it's called the High Energy Astrophysics Division of the American Astronomical Society. And so they have an annual meeting. And of course, they knew any eclipse was coming. So they booked a hotel that was pretty close to center line. So the astronomers should get a good look if they want at totality in Sun Valley, Idaho. And I believe the time of totality was on the order of 5 minutes at that particular spot. So it was pretty good. So yeah, I will be traveling to see it. And of course, if you get an opportunity, you should see the eclipse. If you can do it live, wonderful. If you can't, I'm sure there'll be thousands of cameras pointed toward it and telescopes. And in fact, one of the things I posted on the discussion board was this interesting project between Google and, for example, Berkeley, where they're inviting everyone to take a picture on center line or off center line of the eclipse and go ahead and send it in. And so it's a citizen science project, and they're calling it the Mega Movie or something along those lines. But it was pretty cool. So if you do get a chance to see the solar eclipse, do so. They're kind of fun. They're a lot of fun, actually. So I think this will be my, well, I'm so young, this will be my first one. How about that? This will actually be my 4th solar eclipse that I've seen. Not because I've traveled to see them all. This is actually the first one I'm actually traveling to see. Otherwise, they just happen to be wherever I'm at. Looks like you got a map up, Becky. And you have to take the mute off your microphone.
I was typing all over the place and didn't want it to switch over to me. You can hear me now, right?
Yep.
Okay, cool. So I should have looked. I did not get a world map. I got a map of the United States. But if you live somewhere close along this like big yellow thick line, that's where you're going to be able to see the path, like the total solar eclipse. But if you're anywhere like on the continent, like this just means that you'll see 90% of the sun block. This is like 80%, 70%. So you'll still be able to see something of the solar eclipse, but it's only if you're along this path that you're going to be able to see a total eclipse.
And I was wrong about the time from that map. 2 minutes in totality, roughly.
Yeah. So.
Short and sweet.
Yeah.
Cool.
It's definitely different than a lunar eclipse. Lunar eclipses take hours.
Oh yeah, they're very luxurious. You can go have many cups of hot chocolate before you see it turn copper red, which is cool to do. So
yeah.
But yeah, solar eclipses are bang bang, 2 minutes in totality. The event will last longer than that, but the amount of total darkness is relatively small at 2 minutes. So okay, let's see. Maybe I'll try and cover one other one here. I'm going to do a screen share. So there was one question, can you explain parallax and retrograde? So I'll try. Oh, that's the topic of the lectures this week. I'll spend a little bit more on that, and then maybe we'll pick up another current topic. So I'm going to do a screen share here. Screen share. Start screen share. You see that?
The looks like a bracelet.
Yeah.
Okay. Yes.
Great. So you're right, it's a bracelet, but hopefully you will recognize those as the planets. 1, 2, 3, 4, 5, 6, 7, which is the 7 planets known to antiquity. So the motion of the planets looked really complicated, right? The motion of the planets was a particular mystery that played a key role in the development of civilization. And at some level, it's relatively easy. Like all the other celestial objects, the planets go, they move from east to west. They rise in the east, set in the west every day. Nothing mysterious there. And like the sun, okay, superimposed on that daily east to west motion is a slow drift eastward against the background stars. And this slow drift happens because in reality, Earth is going around the sun. But from a stationary Earth point of view, it looks like there's this slow eastward drift. So no mystery there, right? That's easy. There's nothing complicated about that motion. And so they got that. But on occasion, depending which planet you're looking at, whether it's Mars or Jupiter or any of the planets that undergo retrograde motion, the planet's slow eastward drift eventually slows, stops, and reverses itself, as shown in, for example, the top image there. Follow the arrows, and there's sort of that slow driftward west, and all of a sudden it reverses motion and starts going east to west. It's going backwards before continuing on. And so, yeah, for a while the planets look like they go backwards against the background stars, before eventually reversing their direction and continuing their driftward eastward. And you can tell from the series of 4 images here, it's not regular. Sometimes it loops, sometimes it does go back and forth, but it doesn't loop on itself. Sometimes the loops, the eccentricity of those ellipses is really long. Other times they're kind of shorter and squatter. And so there's a variety of ellipses that they do. And they do it fairly often. And so now this is a complicated motion. How do you describe what's going on there? And so the question that was asked in the book, or in the discussion board, can you describe retrograde motion? So retrograde motion is simply the planets appearing to go backwards, period. That's the observation. Planets go backwards. Now you want to explain that. Okay, that's a whole different ball of wax. But retrograde motion itself is just the observation that planets go backwards. And so retrograde motion required some fairly fancy techniques, circles on circles, to model in an Earth-centered universe. And there's an example of one in the image here. You can see that it's basically almost like a spirograph. And so this looks like the motion of Freya. So I see Freya on there, so that's Venus. And it's doing these loop-de-loop-de-loops as it goes around fairly frequently. That's a very complicated motion. Ultimately, that description is wrong, right? Because we learned that the Earth is not at the center. And so in a sun-centered cosmology, the retrograde motion has a very simple explanation. It's just one planet going faster than the other planet than another one. And you know this. If you've ever driven on a freeway, on a highway, and you pass someone, it looks like they're going backwards. They're not going backwards. You're just going faster than they are. But from your perspective, they look like they're going backwards. And it's the same thing on a highway as you can think of the planetary orbits as sort of lanes on a highway. And so Earth is closer into the sun than, say, Mars. And so Earth goes around the sun faster. Kepler's laws. And so when Earth passes Mars in its lane in the freeway, it makes it look like Mars is going backwards. Okay, so retrograde motion is an illusion in that in the Earth-centered model, people thought retrograde motion was real. It was physical. The planets really did go backwards. And they created a model such that the planets really did go backwards. And so the much simpler of planets just going circles around the sun led to the conclusion that the observation of retrograde motion was just an illusion. It wasn't really there. Okay, so that's a little bit what I wanted to say about retrograde motion. And is screen sharing off? Okay. Are you back on, Becky?
Yep.
Okay. Let's see. We have just a few more minutes. Let's see. What else can we talk about? There
was a question about precession.
Oh, yeah. Go for it. Where do you want me to go? What's rotation? Yeah, there was a different question about the rotation and precession. So rotation is just an object spinning about an axis. Lots of common, everything in the universe rotates, basically. You have to try really hard not to rotate. Stars rotate, planets rotate, tops rotate. So left to their own, things like to rotate. So it just means spinning about its own axis. And precession I covered quite a bit in the discussion board, and I really don't want to go over that there. If you want to see a nifty explanation of that on the discussion board, we talk about tops and the relationship to Earth, and why tops precess in one direction. Tops always precess in the same direction they spin. Earth precesses in the opposite direction it spins. And ultimately that has to do with the direction of the force of gravity that is causing the precession. So that's a little bit more about rotation and precession. But if you want a detailed more detailed discussion, look on the discussion board for precession.
One very easy and basic difference is the Earth rotates once every 24 hours, and it precesses once every 40,000 years.
There you go. That's quite a difference. Okay, what else is happening? Let's see. NASA this week announced another 10 planets that happen to be in their habitable zone. So we're getting closer to finding Earth's twin, or planets that at least have a better probability of finding life as we know it. So yeah, that was announced this week. So this is done by the Kepler spacecraft. So funny thing, we're studying Kepler this week in the course, Kepler's laws. So this spacecraft is named after Kepler because it's looking for exoplanets. And so Kepler was launched in 2009, and to date it's detected about, in round numbers, about 2,500 confirmed planets, and about 600 of those have more than one planet. So in other words, about 600 are multi-planet systems. And at some point, one of the it's called a reaction wheel. You can kind of think of it as a top or a gyroscope, broke on the Kepler mission. But nevertheless, with a little fancy engineering, I don't know if you ever saw the movie Martian, right? How innovative they got. So with a little bit of innovation, they could keep the broken Kepler pointed. You're not going to see as much because it's broken, but nevertheless, you can still see if you are careful with how you move it around. And so this was called K2. So this was the second phase of Kepler. So it continues to discover new exoplanets, and NASA announced another 10 this week that are found to be terrestrial. That means they're rocky. So in week 4 of this course, we'll cover the difference between rocky and terrestrial planets. So we are finally at a point where we are starting to detect rocky terrestrial planets. And as Becky mentioned earlier, if you'd like to be able to know whether those might be habitable for life as we know, you want to be able to characterize those planets, and the best way to do that is with the type of cameras that Becky is building in the near infrared and the infrared cameras. So that was kind of news this week. 10 more planets in the habitable zone, in the Goldilocks zone. So that's very cool.
There was one question that it was not on the discussion for this, but it was talking about Kepler's laws, where every force has an equal and opposite force. So when he was talking about how Kepler's reaction wheels broke, it's like when you're in space, there's no friction anywhere. So if you say have part of a motor that spins in one direction, then the satellite will spin in the other direction in order to counteract it. So just like spinning part of the satellite will cause the rest of it to like change how it's looking around. So it's kind of cool when you're in space, the way stuff can move. It's actually somewhat simpler because it's nothing on the outside is really affecting it nearly as much as the mechanics on the inside. So that was the reason why when the reaction wheel failed, it was difficult, is because it was much harder to keep Kepler pointing the way we wanted it to.
She's an observer. She knows that much better. Cool. Let's see. What else was in the news over the last week or so? Gravitational waves. We now know 3 absolutely confirmed cases. So space-time wiggles around. It's a fabric. You can make it wiggle. And we're starting to detect those wiggles. And so this is going to be this is the dawn of a new way of looking at the universe. And every time we do this, exciting discoveries come out from being able to look at the universe in a totally different way. And so you are partaking in that as we discover gravitational waves. And of course, people want to know if these objects, if you emit gravitational waves, that generally, just like the very first exoplanets were the big elephants in the room, right? The big Jupiter is going very close to their parent stars. You know, the big elephants in gravitational waves is 2 massive stellar mass black holes, so about 100 solar mass black holes merging together. That's going to create quite a signal, and that's what they detected first. So we now know about 3 of these things. But as time goes on, and I'll make the analogy with exoplanets, as time goes on, as your integration time gets longer, you can start detecting smaller masses. So you can start detecting Neptune masses, start detecting Earth masses, and so you can start discovering many more exoplanets as time goes on. And the same thing is going to happen with the gravitational waves. As time goes on, you'll start discovering mergers of black holes that are smaller. You'll start finding out the merger rate of neutron stars, which is one step sort of before it goes down a black hole. It's the densest known state of matter. So you'll be able to get a handle on the neutron star merger rate and the black hole merger rate, and start answering questions like how many black holes are in the Milky Way? How many neutron stars are in the Milky Way? So it's the dawn of a new era, and you were there for the first ones, and now the second, and now the third. So we just announced the third one this past week. So that's very cool.
To switch topics entirely to something that I find interesting. Sometimes I have a lot of people I talk to who don't have a lot of interest in or understanding of astronomy. And as you know, several years ago, they retired the space shuttles. And people are like, oh, that means that nobody cares about astronomy anymore. And it's like, no, in reality, what it is a lot of these private space companies, like SpaceX specifically, are getting to the point where they can launch stuff into orbit much, much more cheaply than we can, and without the ridiculous bureaucracy that we kind of managed to set up around the space shuttles. And so the reason that NASA discontinued the space shuttles is so that they could use all of that funding that they were draining into the space shuttle program to do these awesome projects like Kepler, like the Curiosity rover on Mars, like the Rosetta that's landing on the comet, that landed on a comet, and the mission that went past Pluto, like all of that stuff. The reason, like, that's the cool new cutting edge stuff, and NASA wanted to focus on that, and they just couldn't afford to keep putting something that was so expensive up into space.
Humans in space is expensive.
Yeah, we're amazingly enough not designed to be up there.
Yeah, we are delicate little things. We have to have all kinds of nice stuff around us.
Although
like
interestingly enough, humans do much better in space than, say, other animals because of the way our organs are set up. We're well attached to be able to survive in zero gravity. There's actually a lot of animals can't survive in zero gravity because gravity is necessary to hold their insides in the right place. So we're better designed for space than most. But the interesting part of the thing that I was going for is one of the reasons that it's so expensive to go into space is that in order to go into space, you have this little tiny capsule that we're trying to throw up into space, and it has these massive rockets full of fuel to boost you up fast enough to get you out of the atmosphere. And the most expensive part is that what we used to do is just release those rockets, let them fall, and we just like scrapped them. We never could use them again. And SpaceX is cool because what it's trying to do is land those boosters back down on so that they can reuse them. And if they can do that, they can make it way, way cheaper to put stuff up. And that's like the first step to trying to get people back up easily and to start building stuff, is being able to make it much cheaper to put stuff up in space. It's a scary prospect, though, because the most fuel-efficient way to land boosters is to let them free fall into the last possible moment. So they're going really, 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 really fast. And then they burn all the fuel at the last moment to slow down. So if something goes wrong...
Boom.
So far, though, they've never had it go wrong in that way. It always slows down. It just has a tendency to tip over at the end.
Yeah, I think we're really at an interesting point that... you know, Elon Musk gets the most attention, but he's hardly the only one. Richard Branson has Virgin Galactic going. Jeff Bezos of Amazon has Blue Origin going. So there's a number of private space companies getting into the business. And that's never happened before. So this is pretty interesting. I don't know where it's going or what will happen with it, but it is a development. And a pretty cool one.
And Virgin Galactic is cool, it's cool for private citizens, because the point of Virgin Galactic is basically space tourism.
Cool.
People can buy tickets, go up and be at the very edge of space for several minutes and then come back down. It's an expensive ticket right now, but it'll go down, you know. In our lifetime, it might become something that you can actually afford. So,
do you want to go?
If I had the opportunity, I'd go.
You would go.
It's like, yeah, it's like most people who go into astronomy and astrophysics, it's like deep down, we all hope someday we go into space. It's like, that's what you really want, is go into space and explore new places. It's like, you know, like a few centuries ago when people used to get on ships and have no idea where they're going or if they could ever even get there and they might die. Nowadays, the only place that you can do that is by going into space.
Yeah. Cool.
So
that is awesome. And on that note, I think that's a good place to end this opening YouTube #1. We'll be having a #2 in about 4 or 5 weeks. And again, we'll post a discussion board thread. You can post some questions up. And by that point in the course, you'll be much farther along. We will have covered gravity. We will have covered light. We will have covered the origin of the solar system. We will be in planets proper. So we'll have done the terrestrial planets. We'll probably be on somewhere between the Jovians and then the ice giants out front by the time we have our next YouTube. So we'll be much farther along in this course, right before the final, actually. It's 1 week before the final exam. Becky and I will do it again. And of course, there'll be a lot more astronomy news and questions that you'll have, and we'll have fun with it. So thank you very much for joining. And if you're watching the recording, thank you again very much. Remember to ask questions on the discussion board, and Becky and I will answer them. And we'll go from there. Okay, thank you.
Bye, guys.